Hello everybody, my name's Dan Tech. I'm a PhD student at the University of Leeds, and today I'm going to be talking to you about relating seafloor geomorphology to subsurface architecture, and specifically how mass transport deposits and nick point zones build the stratigraphy of the deepwater Hikurangi Channel. Now the results presented here actually form part of a publication that was recently published in Sedimentary, so if you're interested in anything that I present here, please check that out. So as it may have been evident from the title of the talk, one of the aims of this study is to integrate bathymetry and 3D seismic data to link seafloor geomorphology and subsurface architecture in the Hikurangi Channel offshore New Zealand. And on the right you can see a map of where the study area is located. So we've got the around 2,000 kilometre long Hikurangi Channel, and this is a sort of 150 kilometre long stretch of the Hikurangi Channel located just downstream of the feeder canyons. And then the second sort of aim is to investigate how seafloor features like channel damming mass transport deposits and upstream migrating nick points can build channelized stratigraphy. So just a conceptual introduction, I'm going to be talking quite a lot about nick points and nick point zones. So nick points are steep steps in a channel's longitudinal profile. So you can see the profile at the bottom. We have defined increases then decreases in the channel's longitudinal gradient. And these are sometimes organized into nick point zones, which are overall the closely spaced areas of nick points that overall constitute a larger increase in gradient of the longitudinal channel gradient. And on the right we can see them in plan view, and these features are usually U-shaped or V-shaped in plan view, and they widen downstream. So the first step in integrating seafloor geomorphology and subsurface architecture is to look at the seafloor expression of the channel. Here you can see around 150 kilometre long stretch of the Hikurangi Channel. It's about 1 to 4 kilometres wide along most parts. It's characterized by a flat channel floor that is bound by steep channel walls. These steep channel walls are stepped and contain terraces, so these are the grey areas you can see on the right, and there's multiple step terraces on these channel walls. And if you take a longitudinal profile through the thawag of this channel, you can see these defined steps or these increases in longitudinal gradient called nick points. And these are often, some of them are organized into nick point zones. So we can see nick point zone 1 and nick point zone 2 here. And just to zoom in a bit further on the seafloor expression, on the left we can see a area of sort of black, steep, scallop-shaped features towards the south of the channel. And these are interpreted to be faults as part of a mass transport deposit that is interpreted to be failing into the channel. So the channel walls have collapsed, caused a mass transport deposit that has failed into the channel. As you can see upstream of that area of scallop-shaped black features, we have a relatively wide and flat channel floor, and downstream of that area of scallop-shaped features we have a relatively narrow one. And this narrow channel floor narrows even further upstream to a point, or to 2 points actually, nick point 1 and nick point 2, and these form nick point zone 1. And downstream, so in the figures on the right, we can see multiple scars which are interpreted to be previous channel wall failures, and some terraces on the channel walls, so we can see this relatively complex terrace channel walls here. And step 2 in integrating subsurface architecture with seafloor geomorphology is to look at the subsurface. So the subsurface deposits of the Hikurangi Channel can be divided into 4 depositional elements, which I'll take you through now. Each of those depositional elements can then be further subdivided into multiple seismic facies. The first depositional element we have here is channel fill, which comprises generally high amplitude reflectors that are likely to be sand rich, and these can be divided into 3 seismic facies. Seismic facies 1 are lens-like high-amplitude reflectors or packages of high-amplitude reflectors. As the title says, you can see on the left-hand image below, these are generally lens-like in shape and are hosted with within erosive surfaces that are concave up in cross-section. They are interpreted to be sand-rich channel floor deposits. And something that's important about these deposits and the surfaces that are within them and that host them is that multiple surfaces that are concave up in cross-section and therefore lens-like high-amplitude reflectors within them can exist within a larger scale confining concave up cross-sectional surface which hosts multiple smaller surfaces. So the importance of this will become clear when we get to the discussion. But just keep in mind that you can have nested scales of concave up in cross-section surfaces in these deposits. And then seismic facies 2 are flat, wide, high-amplitude reflectors, or packages thereof. And as you can see on the top right seismic section, these are interpreted to be wide, sheet-like, sand-rich deposits that have internal amalgamation and incision, so they will contain sort of concave up in cross-section surfaces, but these will be below seismic resolution, so they present themselves as one large continuous high amplitude reflector or packages of. And then seismic facies 3, we have inclined, unilaterally stacked medium to high amplitude reflectors that generally stack next to each other and dip in the same direction. And we can see these on the bottom right hand seismic section here. And these are interpreted to be the laterally stacked margins of a channel that has migrated in one direction over time and preserved deposits of one margin preferentially as it's migrated. Second depositional element, terrace or sheet deposits. These are characterized by tabular reflectors and are likely heterolithic. These can be split into two seismic facies based on their relationship with their bounding surfaces. So we've got non-truncated tabular reflectors, which are reflectors that are bound by a U-shaped or a concave up surface on both sides. So both margins of the reflectors terminate against a single through-going surface. Whereas truncated tabular reflectors are their outboard side, so the side away from the channel, terminates against a concave up surface, but then they're truncated by a younger surface that basically cuts them. So the different interpretations of these, non-truncated tabular reflectors are interpreted as sheet deposits or like late stage channel fill, and the truncated tabular reflectors may be incised sheet deposits, so incised versions of seismic facies 4, or they may be terrace deposits formed by internal overspill onto a raised platform above a new conduit. Levees, this is relatively simple one. These are continuous, laterally continuous reflectors, also likely heterolithic, and these can be with sediment waves or without sediment waves, and these are basically outside of the wider channel belt and outside of the deposits that continue for tens to hundreds of kilometers away from the channel. Tens to over 100 kilometers, I should say. And finally, mass transport deposits. These are characterized by three main seismic facies. So we've got transparent chaotic zones without really much reflectivity in them at all. And these are interpreted as slumps or debrites dominantly. Then we have folded and faulted reflectors, which have internal reflectivity, but they are deformed. And these are interpreted as slump or slide deposits. And then we have basically blocks of coherent reflectors that aren't very deformed internally, but are sat within a surrounding area of the other seismic facies, other mass transport seismic facies, and these are interpreted as megaclasts. So based on the identification of these seismic facies and depositional elements, the subsurface can be interpreted, and I've got a few cross sections here to show that basically going from seismic to interpreted depositional elements. And then once we have those depositional elements, we can then start interpreting the relative ages and doing a three-dimensional chronostratigraphic correlation, defining the relative ages. And the key mechanism by which these ages were correlated was the tops of these mass transport deposits. And on the base of this correlation, we could trace 10 channel forms across the study area and map them across. This integration of the subsurface with the chronostratigraphic framework and the seafloor observations can allow us to build an evolutionary model, which I'll take you through now. So in A here, we've got a pre-existing channel conduit through which flows are flowing. And at some point, the walls of that conduit collapse and they partially block and fill the channel. So this mass transport deposit dam creates a decrease in longitudinal gradient upstream of it, causing partial ponding and the deposition of flat tabular reflectors upstream, and then downstream an increase in longitudinal gradient causes a knickpoint zone to form, which then starts to migrate upstream. As this migrates upstream, it incisors through the mass transport deposit itself and the partial ponded deposits that formed upstream of it. And eventually, as that goes even further, the channel reattains equilibrium and the knickpoint zone may die out upstream. So just a summary of this evolutionary model. First, we've got the collapse of a channel wall the formation of a mass transport deposit. Then we've got the formation of partial ponding upstream and knickpoint zone formation downstream. This knickpoint zone migrates upstream and sequentially incises the mass transport deposit and the ponding and the deposits formed upstream of it. And then eventually the channel reattains equilibrium, and we've got this sort of new channel form with bound by terraces. And in comparison with more traditional cut and fill models, which invoke large scale aggradation or filling of the conduit and then a degradation along long reaches of the channel, we can see that can also generate a very similar motif to the one that we have just seen there in the previous image. And a comparison between the two. In the top one, we've got more localized processes of mass transport deposit damming and knickpoint zone formation, migration upstream. And in the lower section, the cut and fill model, we have basically over the entire reach of the channel that we've shown here, there is an overall filling and then an overall cutting and then widening of the channel, and both can create relatively similar geometries. So just to finish up the discussion section, if we think back to before in the depositional elements section when I was talking about how the channel fill can host multiple concave up surfaces and lens-like high amplitude reflectors that cross-cut one another, and that all sit within a single channel fill deposit or within a master concave up surface. So multiple small-scale concave up surfaces within a larger master surface may be interpreted as or termed stratigraphic hierarchy. However, this hierarchy may arise from multiple different mechanisms. So, in the top example we have here, we have a schematic showing what looks like hierarchy can be generated by the passage of multiple upstream migrating nick points. So as each nick point migrates upstream, it erodes upstream and deposits downstream, leaving behind a filled concave up surface that is elongate downstream. As more nick points migrate past that point, more concave up surfaces are generated that are sort of cut into previous ones and that are located laterally offset from the previous concave up surfaces. This process causes the progressive widening and deepening of a master surface that hosts the whole channel fill deposit, so it hosts the deposits of multiple passing nick points. And So that causes a larger concave upsurface to host multiple smaller concave surfaces. Alternatively, erosion along long stretches of the channel that generate, again, U-shaped conduits, which are then filled in a more conventional cut and fill manner. So you've got alternating periods of incision and then infill over long stretches of channel. And repeated cutting and filling, or incision and infill, can cause a progressive formation and the widening and deepening of a master concave upsurface that hosts smaller scale concave upsurfaces, hosting the deposits of each incision or each channel formation. So we've got two contrasting mechanisms for the formation of the sort of same stratigraphic pattern here. So just two sort of relatively simple take-home messages from this talk, really. Firstly, MTDs from channel wall collapse and their clearance by migrating nick points and nick point zones can generate surfaces and stratigraphy in deep water channel systems. And secondly, nested scales of elongate concave up surfaces can be generated and filled by migrating seafloor features. I'd like to say thank you to the sponsors of the TRG and to Western GECO for providing the data. Thank you very much for listening. I'll take any questions.
So that was a great talk from Dan. Thank you for that. The data is beautiful. It's really nice seismic data you've got there. So I'm gonna keep a lookout for some questions from the audience. In the meantime, I have one or two that so I think the first one is, do you think that the nick points would have formed without the mass transport complex? Do you think that if it hadn't been for that, then you wouldn't have this nick point formation and then overall, you know, deepening of the channels?
Yes, it's a good question, and one that I really don't know the answer to be honest. So we've suggested a few mechanisms for forming these things. So first of all, being essentially just large, and these are also proposed by other authors as well. One of them being just like a large cyclic step. Then the other one is, you know, what in our model, the nick point zone is created by the mass transport deposit on the downstream side of that, whereas and that contains multiple nick points. So whether they're internally generated by some sort of flow mechanism, whether I don't really know, or whether they are basically, or whether nick points outside of those nick point zones are basically remnants of nick points that were related to mass transport deposits that have just migrated elsewhere and are now present outside of it. I don't really know. Okay. But it's a good question, and we kind of need more constraint on the seafloor side of things to answer that one.
So we don't seem to have any other ones, so I'm going to ask another one. So the other thing I was going to ask is, there's been a few presentations I've seen recently where people, and this could be subseismic to be fair, this might not be the resolution of your data, but there's been a lot of people who said that, you know, you see this difference in the channel sinuosity as you move across the mass transport complex. So I'm just wondering if like one of your channel fault legs have actually straightened as a result of the mass transport complex and then subsequent nip point.
So this is, I think, the difference between, I think I've seen similar things. I think Jake Covalt did a talk a few weeks ago about a similar thing from offshore New Zealand. Yeah. So what's different about this situation is that the mass transport deposits are coming from the channel wall, which means that they can never fully block the channel and therefore cause like avulsion or anything like that. So what's happening here is more of like a, I guess, the mass transport deposits will sit within the channel. So rather than a channel being responding to the topography that it's on top, it's more like the mass transport deposit is within the channel itself. So the sinuosity won't necessarily be related to the topography on top of the mass transport deposit. However, what is interesting, and something that I'm trying to look into now actually, is by mapping the distribution of the mass transport deposits, what effect does the channel wall collapse have on the generation of sinuosity in the long term? So if you have long-term repeated failures on the outside of a meander bend related to, I don't know, undercutting on the outer bank or something like that, is basically the repeated failure and mass transport deposit generation on that outer bend the mechanism by which the channel increases sinuosity through the long term? And I think it's an interesting question that I'm still trying to answer.
That's pretty cool.
Yeah, I have a question actually, because you know, again, being a continental to shallow marine person, I'm a bit outside my realm here. But I was wondering if these the density of these mass transport deposits were related to the position of major faults and fault activity in the subsurface, or are they just randomly distributed and it's just, you know, slope failure because they're just too steep and they just collapse at some point?
There aren't any faults. Can I share my screen to like show things, or is that time past?
No, go for it.
Okay, so can you see this aims and objectives slide? I think we can,
Yes.
right?
Yeah.
Okay, right. So if we zoom in a bit on the figure here, so this is the sort of area we're looking at, and actually that is quite separate from the folds and thrusts that are in the accretionary wedge. So it's actually more within the trench. The causes of these mass transport deposits is, again, something we're currently investigating, because there are multiple sort of potential factors that could come into play. First of all, we're on a very tectonically active margin, so whether big earthquakes could play a factor in that. There's also an abundance of gas hydrates in the shallow subsurface within the data set that we can observe. So whether the dissolution of gas hydrates might have an impact, whether, like you say, it's just they get too steep because of outer bank undercutting. They're all options, they're all fair game, and I'm trying to figure out how to determine which one is the smoking gun, but I don't, or if any of them are, and I haven't. Maybe in another talk I'll give an update on that. Hopefully.
Yeah, cool. Cheers. We have Regit. Oh, you just answered the question actually. He was asking about, do you think gas hydrostability dynamic? Maybe. Yeah. There you go.
Very possibly.
Yeah, no, yeah, the figures and as Emma said, the quality of the seismic data, but the quality of the figures in that paper are also, yeah, it's a beautiful piece of art. Let's put it that way. I think we can all agree on this. Yeah, do we have anybody else you see? Anybody else from the audience have a question? I'm going to try to conduct the same analysis you've done on other channel, for example, on some channel on the other side of the island, and you know, not in the trench, but what's the name of that? You have some funky channels on the other side of the New Zealand island.
I guess there's the Taranaki Basin, which has some very nice buried channels in, and on the yeah. I mean, ideally, I would love to do more investigating into this sort of channels offshore New Zealand. Whether I'll have time and money to do any of that is the big question. There's also sort of question, which I think some of the people from NIWA, the New Zealand Institute for Water and Atmosphere, are looking at more, is that actually these channel wall collapses or canyon wall collapses in the canyons are a lot more common if you go towards the more proximal regions. So if you can see these like blobs, this is data from NIWA, the New Zealand base, and you can see these like sort of blobs which I interpret as basically scars and mass transport deposits from canyon wall collapse. So it's quite a big, probably quite a big process on this margin, I think.
Yeah.
In particular, so getting data from other margins and other places around New Zealand would be absolutely ideal in order to do maybe some statistical comparisons on them and really sort of cement their importance into rock record.
Yeah, no, this is great stuff. I remember, Jake Cavell, after his talk on SEDS Online, he showed us a few cool bathymetric data from New Zealand. It's amazing. It is incredible what you guys can see with this data.